This section is going to be dealing with file organization. Now, as we write C programs, we're going to write the program with the main function, and generally there's always going to be a number of other functions associated with our program. The idea is, when you look at any program, if there's code that repeats itself, this code lends itself to be broken down into a function so that you've written it once and then you call it a number of times. This is good program organization, and it makes for cleaner code. But as you start writing more and more functions, when you're writing this, having this all in one file, one C file, then becomes kind of clunky and very hard to maintain. So the idea here now is we're going to be talking about file organization. And let me take a look and see if I can't illustrate this a little better. So say what we've got here is that we've got our main program, and here's our main function. And then there's going to be function 1 is going to be in here too, and then function 2 will be there. And we'll say function 3 and function 4. Now if all of this is in one file, imagining then any kind of a change, you're going to have to go into the main file and change it, and you're going to have to compile the entire program. So the concept here of file organization is to recognize and breaking these down into good logical units. So what you would have is you'd have one C file for your main. You'd have maybe another one for F1. Maybe one will lend itself to putting F2 and F3 together. Because again, the concept isn't a breaking down into every function has its own file, but again, where it has some logical meaning to the grouping. And then we'll have function 4 here in its file. So we look at this now, and what we're going to end up with is we're going to have, in this case now, we look and we see we're going to have 4 different C files. The nice thing about this then, if you're going to make a change, say you make a change to just something in the code here in F1, then all you do is you recompile that and then you link it together. Now to do this, as we're going to see, we're going to have to tie all of this together, and so we're going to have header files. And our header files are going to be able to then section this out and put this down into more meaning. What we're going to do is have a header file that might list all of our function prototypes, another one that has our other includes. Looking at this again, trying to break this down as much as you can into logical order. Now, ideally, your main program should be nothing more than a control. No processing should go on in a main program. Basically, all this should be is flow of control and then calling the meaningful sections. Likewise, ideally, your main should only have one include. So include your overall header, and inside of there, you're going to have includes of all of your other headers. Now, this is the ideal and the goal, and sometimes it works out, sometimes it doesn't. So it's not that this is going to be a hard, fast rule, or in this course you must do it, but it's something that as you see and we start talking about program organization, this is something that you should aim for. So a good main program, again, nothing more than just control, do A, and then do B, and then do C, and then in it again should have just the one include, and that include header is going to have all of your others. So let's take a look and see if I can show you what I mean by this. So we go back to here, and here we've got a main function. Let's say we're going to do this code a number of times. Let's say what we're going to do is we're going to be doing our division, and we do it repeatedly. So what we want to do is, instead of writing that same code every time, we want to just put that into a function, break this out, so that we can call it just that. So I'll look into here, and now what I've done is I've broken this down into a function. I have my main again here. My main program is the same, but now this code here has been broken down into its own function. And what I've done now is I've logically broken this down into manageable pieces. And again, this is the goal of what you want for a good C program. Now, how do we use this? I've got the function. Let's take a look at this. And the goal now is to break down the main program into other functions, and then to put those other functions into separate files. Now again, we can put this all in one file, and this would kind of work. We're just going to see order matters. But the idea here, though, is to make this into logical units. So I'll break this out. I'll create a brand new C file. I'll call it functions.c. And then what that's going to do is have that code, and now my main.c stands alone. All of the code in my main function is in one file, and then the function division is in its own file. Having done this now, this is going to produce an error. If I just do this and link this, the code will compile and run, but the answer is going to be incorrect. And why is this? The preprocessor doesn't know what the return type of the function division is. We look at this, and this is going to be of type float. But at this point here, the preprocessor does not know what this is. Here's division, it's going to return, but it doesn't know the return type. So it's going to assign it the default type of int. This is what the compiler does. If in doubt, everything's an integer. So running this code is going to return the value of 4.0 and not the actual answer that we want. So how do we correct this? We must prototype the function. We must do this until the preprocessor knows there's going to be a function later on called division. Its return type is going to be float. Once we tell the preprocessor this, when it gets to this stage, it knows now that the return is going to fit exactly what the assignment location is. Now we do this by doing a prototype. And what a prototype is that if you notice what the function is here, all we do is we put the prototype in. Now there are two differences to note, and these are very important. You may or may not, this is optional, you could actually put the names of the variables in there. A lot of programmers do not. Again, this makes it for more readable code, but syntactically you could do either. But the other thing, which is mandatory, on the prototype you must finish this with a semicolon. You notice here, obviously, when you've got your function calls, your function leaders there is no semicolon. But when you prototype, the prototype must have the semicolon. Otherwise, again, your program won't compile. Now, the preprocessor, because this has been prototyped and shown before it's actually used, now the preprocessor knows exactly what the return type of division is going to be. Now everything's all rainbows and unicorns. You're ready to move on. So the list of prototypes can get very large. Imagine as your program gets bigger and bigger and you have to prototype each function before it's used in the main. This can have a number of prototypes in it. So when it gets larger, the solution to this is going to be create a header file specifically for the prototypes. So what you would do is you'd break out, and this is what I meant about having a header files that tie everything in. One of your header files is going to contain your prototypes for your program. It can contain your macro divisions, your data types, and your variable definitions. Now, all of this can go into one header file, or again, as your program gets increasingly larger, you may even want to break these up into their own separate headers. Again, now we're talking about file management and the idea of putting this into the most usable formats that you can. So looking at this, let's look at a header file. What I have as the header file here is I'm going to declare a global variable called RT, and here I'm going to have my prototype for float. Now if I call this header file here before the actual main program, remember what the include does. The include goes and then will actually find the code that's in the H that I'm talking about, the header file, and actually puts that code in. So this is the exact same thing as if I typed this in that location. And that's why it's important. And we're going to see order matters. Order matters in your includes, because if you get this out of order and you include one and the other definition is beneath it, the preprocessor will not know what to do. So I'll get back to that again or remind you again, but this is very important. Order matters. Now looking at my header file again, I also have my preprocessor directives. Look here, and I've got my if n defined. And what that is now is I'm going to have a variable called program space -h dash include. And what the preprocessor does is it comes here and says, has this been defined? If this is not defined, then we're going to go in and do this code. If not defined is false, in other words, we've already defined it, it's going to skip this. We do this so that these are not defined over and over. Say, for example, somehow you've cascaded this into other header files. Without something like this, it may turn around and try to define these over again. And since this global has not been declared as static, it's going to consider that and overwrite that example of that global. So we want to avoid this. We avoid it again with our preprocessor command, our if not defined. So it goes and if not defined. If it's true that's not defined, first thing we do, define it. Obviously now, next time through, this has been defined. So we go in, and the first thing we do is we do the preprocessor directive of defining that variable. We define this constant, and we define that, so now it's done, and then we go and we add the 2 lines. Again, see what's happening and understand why this is very important, why you want this in all of your headers. This way, your header is never going to be defined more than once. It's not going to be included more than once when you're doing the linking. So we move on here, and what I've got is, say you want to also have a variable definition. I want to have an alias for int, and I want to call that num. I would put that also again inside of my header file. Instead of putting it here, I would put it into my header file, because again, it's the same thing as if putting it there, but this is cleaner code organization. So now what I've got is I got my functions.h, or could have been functions.c. Again, when you're creating your library can either be your header files or it's going to be a collection of C files. If this was a C file, then we would compile it differently than an H, but other than that, it's the same. The reason you would do this is depending on how you're building your library. So looking at this now, I also have got my definitions header.h, and here are all my definitions. And so what I want to do now is I want to include a main header. I'm going to create an overall header that's going to be able to deal with these 2 headers. What does that look like? Here's my main header. And again, now this is what I'm saying about breaking this down into logical units. Instead of having 5 or 10 or 20 includes in my main, I've got just the one. The one there then says here, define this. It will go into main header, and look what's there. Oh, look, those are include statements. So it goes and it includes this, so it'll include the definition header file, and then it'll include the functions.h. So in this way, what I'm doing now is I've got my just one header there, but it's cascading and it's building on. Again now, the goal of breaking this into logical units of work. Looking at this now, this is the program that I have. Ready to compile, everything is in the correct order, everything's included, and I have ensured things are not going to be double included. So everything now again is all rainbows and unicorns. This is what we meant. We talked about compiling, we talked about the linking stage. This is what we meant by the linking stage. All of your separate C files have been turned into object code. It includes all of the other header files and all your library functions, either your built-in or the library functions you do. It gets all of those and puts that together, and this is what creates your final executable. Looking at this then, again, your library code that either is code you've created and you've put aside, you'll find that as you did more and more programs, there's going to be certain functions you use over and over in a different variety of programs. Well, you put that into a library. You don't reinvent the wheel. You don't retype in if you don't have to. So you do this, and again, you've compiled this into object code already once upon a time. That is in your library. So that ends the idea of putting together all of your programs and doing some file management on your C programs.